Welcome to the Mechatronics Revolution Fundamentals and Core Concepts. In this lesson, we'll talk about MOSFET transistors. The learning objectives of this lesson are to first describe the operating principle and key specifications of MOSFET transistors. We'll then explain the purpose of MOSFET switching circuits, and we'll talk about the key circuit elements in these types of circuits. Finally, we'll illustrate a MOSFET switching circuit for motor control. When we think about mechatronic devices, it's important to understand the difference between high power elements and low power elements and how they interface together. A typical load in a mechatronic device would be something like a motor, a servo, an LED, or something like that which requires relatively large currents. We call these things loads. For instance, a motor may draw somewhere between hundreds of milliamps all the way to maybe 50 amps or more. An LED may draw 20 milliamps, 30 milliamps, something in that range. Now, those current levels are much higher levels than microcontrollers typically operate at. So typically, a microcontroller is going to operate at a much lower current level. For instance, the maximum current that you can draw from a pin of the MSP 432 microcontroller is 6 milliamps. That's the maximum current you can draw from this microcontroller. So if you try to power a motor directly from this microcontroller, you would burn it out. So you don't want to directly power any high power loads from a microcontroller, and likewise you don't want to sync those high current values into a microcontroller. So that can break the microcontroller. So a microcontroller or an embedded computer is considered a low power device, and sometimes those are called logic level devices. High power devices or loads would be things like motors, servos, LEDs, pumps, or other types of actuators which draw currents that are a lot higher than microcontrollers can handle. Now, transistors are often used to create an interface between the high power elements in our mechatronic device and the low power elements like our microcontroller. So this is a typical diagram of how something like that might work. We have our logic level device, our embedded computer or a microcontroller, and the outputs of this microcontroller would then flow through transistors. And those transistors are then used as the path for those high current values that power the load. So the high currents that power these loads flow from a power source through the transistor to ground. But those transistors act like switches where the switching element is activated by the microcontroller. So that dashed line there is kind of the high power, low power interface. We'll talk about a particular type of transistor in this lesson called a MOSFET transistor. And these MOSFET transistors are commonly used for these switching purposes or in this high power, low power interface for a mechatronic device. Now, unlike a BJT transistor, MOSFETs use voltage as a switching signal rather than current. So for a BJT transistor, that's a current control device. For a MOSFET transistor is a voltage control device. So a MOSFET transistor is a voltage control device where the voltage supplied at the gate of a MOSFET determines whether current flows between the drain and the source. So here's a diagram of an N-type MOSFET. So this N-type MOSFET has a drain and a source, and usually the current for your load will flow from your drain to your source. Now the gate of this MOSFET, that's where you would interface your logic level device to control the resistance from the drain to the source. So looking at the key states of a MOSFET, the MOSFET has two key states of operation. It has an off state and a saturation state that sometimes we'll refer to as on. Those are the two states we really care about for mechatronics applications. The state of the MOSFET, whether it's off or on, depends on the voltage that's applied to the gate. In the off state, the drain source resistance is very high, and that means that we're not going to see any current flow typically, and that would be like a switch in an off position. In the saturation state, the transistor's on, meaning the drain source resistance now is very low. And that means that current flows from the drain to the source almost unimpeded by the transistor element. So that's essentially like a switch that's on. The internal resistance of the MOSFET at the gate is actually very high. So that means that current is not actually going to flow into the gate from your logic level device. And that's what allows us to separate our load paths or our high power elements of our system from our logic level devices or our low power elements. The fact that the gate internal resistance is so high means that we won't draw much current at all from our microcontroller when we want to turn a load on. There's several important values that we should know about when specifying a MOSFET transistor for a particular application. The first is the gate source voltage. Now, there's a certain particular value of that gate source voltage. That's the voltage difference between the gate and the source. The gate source threshold voltage is essentially the value that we need to raise the voltage above in order to put our transistor into the saturation state. So that value is critical because when we turn that voltage, that gate threshold voltage, say from 0 above that threshold voltage, that will turn our MOSFET switch on, so to speak. Likewise, the drain source voltage is another voltage that we care about when analyzing the operation of a MOSFET in a circuit. Also important to know that the MOSFET acts like a switch, but it has extremely fast switching times. When you switch from the off state to the on state, if you apply a voltage initially at ground and then you immediately raise it above the threshold voltage, the switching times from off to saturation are usually in the nanosecond range. So these switch essentially instantaneously for the types of applications that we care about. Let's take a closer look at a MOSFET switching circuit. So we said that MOSFETs are commonly used to switch on something like a motor, an LED, or some other high power load to switch that load on and off from a logic level device like an embedded computer or a microcontroller. So MOSFETs act as a barrier between the high power portions of the circuit and the low power portions. Here's a diagram of a typical motor driver circuit using a MOSFET. Now we can see the MOSFET with the drain, the gate, and the source labeled. The drain is connected to a motor and a flyback diode, and we've already talked about the purpose of this flyback diode. Past the flyback diode, the motor is connected to a high voltage source that will allow the motor to operate once the MOSFET is in the on state. We can see that the source of the MOSFET is connected to ground, and the gate of the MOSFET is connected to this voltage labeled Vin. Now Vin is our digital logic input from our microcontroller. So it's either 0 for ground, or it could be at 3.3 volts for logic high, or 5 volts for logic high for other types of microcontrollers. And it just depends on the type of microcontroller, whether it's a 3.3 volt high signal or 5 volt high signal. When Vin is above that gate source threshold voltage we talked about, then the transistor's on, and the drain source resistance, the resistance between the drain and the source of this MOSFET, is very low, usually less than 1 ohm. And thus, there'll be a current path that will allow the motor to turn on. So current will flow through the motor, and that motor will turn on. Now when Vin is then set below the threshold voltage, the drain source resistance all of a sudden becomes extremely high, and now no current is going to flow through the motor because that drain source resistance is so high that's essentially turning a switch off or disconnecting the high power portion of the circuit. We already mentioned that the flyback diode protects the MOSFET or the switching device from a large voltage buildup. So when that MOSFET switches from the on state to the off state, we get that voltage buildup because that motor is a high inductive load. As a result, if we didn't have that flyback diode in place, we would get a huge voltage drop across the drain and the source, and that might blow out our MOSFET. So that flyback diode provides an alternative path for our current, and our current kind of dissipates in a loop there and is dissipated to heat rather than flowing through our MOSFET and potentially burning it out. It's also important to ground our gate terminal. You'll see a resistor that looks like it's between the VIN input and ground. And what that's going to do is make sure that when we set our input to logic low, that we completely ground that gate terminal, and that's going to make sure that we turn that MOSFET completely off when we want to put VIN to ground. Let's look at the specifications for some example MOSFETs in this chart. MOSFETs come in a wide variety of sizes designed for different applications. So here's three different MOSFETs of significantly differing capability. And I've labeled some key specifications from the spec sheet for these three devices. First, we can see the on resistance. So this is the resistance between the drain and the source when the MOSFET's in the saturation state. You can see we're talking about 1 ohm, 2 ohms, or well under 1 ohm. So this essentially acts like a closed switch when in the on or saturation state. These resistance values are very low. Some of the most important specifications are the maximum drain current and the power dissipation values. This tells you what maximum current you can put from, through your MOSFET from drain to source. So a low power MOSFET would be like the top example where we have 115 milliamps maximum drain current. A typical motor might draw 1 amp or 3 amps, and so that MOSFET isn't going to be able to provide the current value needed to run a motor, for that type of motor, for instance. As we start to look at the other MOSFETs, we can see we have a 4 amp maximum and a much higher current maximum for the third MOSFET, and these MOSFETs are really designed for high power loads like motors. You can also see the power dissipation value, and MOSFETs, because these high current values are flowing through them, they will get hot and they will dissipate power. And so if you're not careful to make sure that they have the proper power dissipation rating, then they can get too hot and burn out. So you want to make sure that you calculate the current through your MOSFET as well as the voltage drop across the drain and the source to then arrive at the power dissipation value for your particular application, and make sure that your MOSFET has a proper power dissipation rating above the value you calculate. You can also heat sink your MOSFET to mitigate that heat buildup that you'll see. The final value in the final column in this table is a gate threshold voltage that turns the MOSFET on. So if you're using a logic level device that goes between 0 and 3.3 volts like the MSP432, then you can see that when you send a 3.3 volt logic high signal, well, that's higher than the 2.1 volt threshold voltage for the first MOSFET and the 2 volt threshold voltage for the third MOSFET. So that will turn that MOSFET, put it into saturation, and it will essentially be like turning that MOSFET on. Now the middle MOSFET, the one that requires 4 volts as the gate threshold, that will only work if you put a logic high voltage higher than 4 volts. So if you're using, for instance, an Arduino microcontroller, which uses a 0 and 5 volt logic high signal, then that 5 volt logic high signal will work with that middle MOSFET, but the MSP432 will not put that MOSFET into saturation. Now that we've talked about building basic motor driver circuits using MOSFETs, let's see an example of one. So here we have the same basic motor driver circuit we've been talking about in this lecture, where we have a MOSFET, we have a flyback diode, and instead of driving the gate of the MOSFET with a microcontroller output pin, we'll just drive it with this switch, which will set the gate of the MOSFET high when we close the switch. So we also have our motor here, which is hooked in parallel with the flyback diode here in black, and we have our battery. This particular MOSFET is an N-channel MOSFET, the IRF 530. Let's watch it work. So when we close this switch, we'll see the motor turn on because we put the transistor into saturation by setting the gate high. And then when we open the switch, the gate goes back to ground and the motor turns off. So that's our basic motor driver circuit implementation that we've been talking about. Let's summarize what we've learned in this lesson. A MOSFET is a voltage-controlled transistor, and it acts as a solid-state switch used often in mechatronic devices. We use MOSFETs to switch on high-power loads like a motor, pump, LED, or servo. We switched on those devices using a microcontroller digital output. And that's really the benefit of a MOSFET. The key specifications for MOSFETs include the gate source threshold voltage, the maximum drain current, and finally the power dissipation rating for the specific device.